All right, thank you very much. Finally the slide is up, so let's dive in. Okay, what this talk is about. Sometimes, the best way to figure out about the future is to look back in the past, right? So that's the spirit of this study. Hello. All right. This is a quote from this German general. No battle plan survives the first contact with the enemy, right? Same applies to space missions. This doesn't mean that there's no point of making a plan. The opposite, you have to plan meticulously. But once your vehicle is launched to space, as I said, many surprises happen. You have to improvise. So looking back the past missions, of course, mission ops acted very wisely to improvise a solution to whatever anomalies they experiences. So this study, ongoing study, funded by JPL, is to, in part, collect examples from the past missions. How did they respond to anomalies? How they adapted to the new situations, and try to extract lessons and derive reusable design principles, hopefully, for future missions. Right, so we interviewed a bunch of people. Then let's dive in to the first example, which is Insight. If you don't know, this was a mission to Mars. One of the goal is to, investigate the heat flow from the underground. So to this purpose, this mole has to be put like 3 meters below the surface, right? So that was one of the two main purposes. So on Sol 82, this mole, this entire structure, the instrument is called HP cubic. It was deployed by the instrument deployment arm, right, to put down on the surface. And this arm, by the way, IDA, is a refurbished arm from a canceled mission, Mars Surveyor 2001. A few days later, HP Cubic tried to penetrate into the subsurface. It couldn't, for some reasons. Why? At that point, they didn't know, and they didn't even know how much depth it penetrated. Only thing it could know was that it didn't achieve the target depth. Why? Because this drill lacked the sensor to measure the penetration depth. Until 0.7 meters, at that point, the mole starts pulling off the tether. And that was the only way to know how deep it went. So that's one of the lessons. Because of that, they could not get the initial diagnosis. So, kind of skipping ahead, but eventually the mission decided to use a scoop at the end of the arm to pin down the mole to help the mole going into the underground, right? And this was a serendipity because this scoop on the arm didn't have any role. It was not a part of the requirement. The scoop was there just because the arm was derived from the canceled mission, and it costed more if they removed the scoop. So you just left there, and magically the scoop came in handy, right? So eventually they tried this pinning down approach. They penetrated a few centimeters. Eventually they could not reach the target depth, but lesson learned, good to have a scoop, right? Another example, Osiris-Rex. As I said at the beginning, it's a sample return mission. Initially, the ground observations suggested that this asteroid would be very smooth, right? So the requirements based on that assumption was said that find a 50-meter diameter patch, free of rocks, lands there at the center, right? Using LiDAR. And initially it thought, no one knew if there is 50-meter spot, but given the information that it's likely very smooth, it's a reasonable assumption. It turned out not. So when it arrived in Bennu, there's no 50-meter patch whatsoever. The only thing it could find is a 8-meter radius patch of a relatively smooth surface. Now, there are two troubles, right? Both are about LiDAR. So the LiDAR resolution was not sufficient. And also there's a concern that there are reflections from the boulders all the way around. So, the automated surface level recognition does not work properly. So what should we do? This is not within the requirements. It turned out that the mission prepared a backup method, vision-based natural feature tracking, just in case. Now, the backup was not implemented because of this, potential rockiness. This was not anticipated. Instead, just, LiDAR development had some risk. So the team decided to, because LiDAR was new in space. So the team decided to have a backup just in case. So the cameras were added at PDR, and this new method, natural feature tracking, was added at CDR, which is unusually late in a typical mission. And eventually, it saved the mission. They used NFT for the touchdown operations, and it achieved 1 meter accuracy. So happy ending. Galileo HEA, this was a famous trouble, I suppose, among space community. Galileo, that was the first Jupiter orbiter launched in 1989. It had the deployable high gain antenna, and for some reasons it didn't deploy. Right? Oh my gosh. So as a solution, these days, whenever we send images from Mars, we use some sort of compressions, lossless or JPEG. That time, data compression was not a norm. And actually, I've heard an interesting story that the scientists fiercely opposed to data compression because that's going to result in some loss of information, technically speaking. But because of the loss of HEA, but fortunately it had other antennas, middle gain antenna and low gain antenna, but with much lower data bandwidth. So it had no way other than using data compression. So, the best way to convince scientists to have anomaly, right? So that was the solution, but the issue was that the main computer didn't have enough memory. Memory had like 32 kilowatts or something. That was a computer back in 80s, right? What saved Galileo was that it happened to have another computer for attitude control. It had two good things. One is that it had extra memory space. The other is that it specialized in floating point computations, which is better suited for data compression. So that was one aspect. Another interesting thing happened to Galileo was that, it was delayed due to the shuttle disaster, Challenger. And as a result, long story, but it had to change the orbit. Initially, it planned to fly to Jupiter directly, but as a result of the change, it flew through Venus flyby, swing by, which meant that it had to come much closer to the sun. So again, long story, but they added the sun sensor, sun gate, to the mission. It turned out that this sun gate was the best sensing method to figure out how much this high gain antenna is open, because they can sense the shadow from different angles, and they can figure out which ribs are stuck. Right? So that's interesting serendipity. And then, so this is kind of opposite to the InSight mode. It had some right sensors. Another interesting thing to mention here was that during the design time, there's a debate whether or not to add the capability to reclose the high gain antenna or not. Mission eventually decided not to add that capability for a few reasons. One is that it required more mechanical switches that they didn't like. And also, I've heard that some guy in the mission said, hey, if we have that capability, we're going to use it. If we use it, then we're going to risk getting the antenna stuck. It turned out that it's the opposite, right? It got stuck. And if we had that recall capability, we could have destuck. So it's a little bit ironic. Next example, Deep Space One and Juno Star Tracker. These are interesting opposite pairs of examples. Deep Space One, that was interesting. I think well-known mission for AI folks. It was the first mission to have onboard sort of AI. At that time, not neural net, of course. It's more like an action planner. What's it called? My advisor was involved. Anyways, so during the mission, Star Tracker failed. What did they do? They reprogrammed the science camera to use as a Star Tracker to save the mission. The opposite happened on Juno. They used Star Tracker for scientific observations that was not intended at the design time. Star Tracker is more sensitive to dark objects than its cameras, Juno Cam. So the Star Tracker SRU was used for for a bunch of different sciences, like imaging the Jupiter's lightnings, dark side images of the moon, and the investigation of the rings. And there's one interesting limitation, though. The data bus between the Star Tracker and CNDH was so slow that it takes 15 minutes to send one image to CNDH. So that limits the data rate. By the way, I forgot to mention, this was possible because, this was definitely not an intended use of Star Tracker, but, Star Tracker is basically a telescope and the sensor, right? And then they had the capability to downlink the images from Star Tracker, raw images, for the housekeeping and the testing purposes. That benefited the mission. Mars 2020 global localization, that was the somewhat new and interesting use cases. So Mars rovers do not have capability to localize itself against orbital maps. Humans do it, but we experimentally implemented the global localization capability on Mars 2020 that compares the rover images and satellite images on board, which works pretty well. And this kind of image processing is not possible on its main computer, RAS-750, because the resource is limited. It happened to have a Snapdragon processor on board. Why? Because we flew helicopter Ingenuity, and it's a base station to talk to Snapdragon, to Ingenuity. And this base station also has a Snapdragon chip. It's a system on a chip designed for cell phones, but we repurposed it for space use case. And after Ingenuity is gone, it's unused. So we used instead for these experimental features. And this localization was successfully demonstrated. Awesome. Except that there is one limitation, that the data bus between Snapdragon and the main computer is so slow that it takes 30 minutes to send the images to Snapdragon. Even though the localization itself only takes 30 seconds, right? So it's a similar theme as the Juno, right? Ingenuity, that's the helicopter. Inclinometer was found broken after the first winter. What they did Well, likely there was IMU, that's kind of similar equipment, right? That's to measure the acceleration, except that, its bandwidth accuracy is different, but that's fine. It's better than having none. So they reprogrammed the computer to use IMU as an inclinometer before the flight. Another adaptation that Ingenuity did was it has two cameras, right? One is for navigation, and that was required. And some guys in the mission insisted to have another camera, which is 4K color camera, even though it is not a part of the requirement. And if you have seen this beautiful aerial pictures from Ingenuity, that was from that 4K camera that's not included within the requirements. But because of that, number one, we could have these great pictures from the Martian sky, and number two, we use the camera for some science, right? Okay, so a bunch of interesting examples, and we can extract some interesting lessons from there, right? One is that we should design hardware level flexibility to be adaptive, like scoop on the inside or Galileo HCA recross capability. We should definitely make the system sensor rich. We should put sensors everywhere, even though you don't have use cases. Examples include Galileo Sungate or InSight's lack of the mole depth measurement. We should design generous margins, particularly when it comes to data, because these days it's cheap to add additional memory or additional bandwidth in your bus, and that could come handy if you improvise different solutions. Make components multi-purposed, like star trackers on Juno or Ingenuity IMU, so that it could be repurposed to something else. And don't try to remove any redundancies you happen to have, right? Again, the scoop in InSight, the extra navigation camera on Osiris Rex, or Ingenuity's 4K camera. So all of these examples happened in the RC 2.0 paradigm. Those adaptations were performed by luck, right? Improvisation. Now, the big question mark for us to solve is how to instead design the adaptability, which we don't know yet. But there are some hints from these lessons, right? First thing we should do is to make our systems, hardware systems, flexible, either having high DOF so that we can change our locomotions, motions. Could be modularized, could be reconfigurable, it should be reconfigurable or meta agent, so that again we can change the behaviors. And our software, right? These adaptations happened manually, ground in a loop, but in the future that should happen autonomously or semi-autonomously. So how we can bring those capabilities on board? That's another question for us, right? Which could be, autonomy or onboard learning, maybe real to sim to real, meaning that you sense the environment, you modify your environment model inside, and then use that model to deploy something to real, or maybe foundation models. My final slide. This is not just technical questions. I argue that it's also systems engineering questions, because we are all familiar with this V model for space systems engineering, which is applied to any space missions from COMSAT in LEO to planetary missions, right? In case of science missions, we have the STM science traceability matrix, which defines all the observations that we have to make. I argue that, when you plan for your trip, right? When you go for backpacking trip, you plan your trip very differently from when you plan your business trip. Why? Because when you go for a conference, you know all the agendas. You don't have to prepare for much uncertainty, But if you go for a mountain for a week, of course, you have to prepare for many uncertainties. So perhaps, we should stop planning the same way for ComSat and partly missions, and we have to figure out something else. Okay, so I would stop here, and I will leave this to an open question to you guys. And then let's invite the final speaker, Anika. All right, thank you very much.